Good morning. In the previous lecture, we had looked at the cross entropy cost function, which looks like the following. J of theta is minus yi log yi hat minus 1 minus yi log of 1 minus yi hat. Today we'll be finding out the gradient descent update rule, basically finding out the gradient of this cost function with respect to the input parameters theta. Again, we need to remember that theta and yi hat are connected in this following way. We first do the x theta, x or x transpose theta given a vector x, that gives us the logits. We pass the logits through the sigmoid function and we then get the probability of class 1. So we stopped at this point. The exercise for us is we want to find out del j theta with respect to del of theta of j. So here I'm assuming that theta is a d-dimensional vector and I'm finding out the partial with respect to a specific jth element in this theta vector. We're doing this to make our calculations easier. Eventually we will go on vectorize this and get del j theta with respect to del theta gradient with respect to the entire theta vector. Now, the way we proceed with this is, and this is, I'm assuming you will try to work this out on your own step by step, is if you look at the cost function, we add a minus sign and then we can write minus yi log yi hat plus 1 minus yi log of 1 minus yi hat. So we can take the minus outside and then do del of del theta j of this summation, where the summation is over the n examples. Now sometimes I write this expression as yi hat, sometimes I write this as sigma theta of xi. Sigma theta of xi means xi is the ith data point, the input features for the ith data point, and sigma theta just means that I do xi transpose theta and I then pass it through the sigma function, sigmoid function. So this is nothing but 1 over 1 plus e to the power minus xi transpose theta. Similarly for this expression we get this. So therefore this expression where we're trying to find out the partial with respect to the jth element of theta can be simplified to something like the following. We take the summation outside and since yi is independent of theta, we move yi outside. Similarly, 1 minus yi is independent of theta, we move it outside. We left with the partial with respect to theta j of logarithmic of sigma theta xi and the same logarithmic of 1 minus sigma theta xi. So you should pause the video at this point and try and solve this for your own, assuming you have done that. Now let's consider this expression as log of some, let's say k. So we're trying to find out del of del theta j of log of k. We can use the chain rule and firstly log the derivative with respect to log k is 1 over k and then you had the k term inside, so then you'll get del k by del theta j. So therefore you'll get something like yi and then this term sigma theta xi and then del of then the partial with respect to this term sigma theta xi, and similarly we do on the other component also. So we already had 1 minus yi. When we find the partial with respect to this quantity, firstly the term inside the logarithmic can come here and then you find the partial of the quantity which was within the logarithmic. Now we should just pause here for a second and look at this aside, which is if we want to find out the partial with respect to the sigmoid function, or what is the del over del z of sigma of z. So to do this, we can again first just expand out sigma of z, which is 1 over 1 plus e to the power minus z. And then you can use your regular calculus to write this as minus 1 plus e to the power minus z raised to power minus 2 and then del over del z of this term. We can do a bit of simplification and we can finally write del over del z of sigma z as sigma z into 1 minus sigma z. So it's a convenient form in which we can write out the derivative. So we're seeing that the derivative of sigma z can be written as a function of sigma z into 1 minus sigma z. Now you should again pause the lecture at this point and you should try and use this result and put it in equation 1 and obtain a simplification for this overall expression. Once you do that, we can see that we can write this entire expression as 1 minus sigma theta xi and sigma theta xi, right? So sigma theta xi into 1 minus sigma theta xi is what you get when you do del over del theta j of sigma theta xi, and then finally you'll also have to do del z by del theta j, where z was sigma I xi transpose theta. So if we just do the same on the other side also, we will eventually, when you're trying to find out the partial with respect to the jth component of xi transpose uh, theta, we'll just get the jth component of the xi. Remember, xi is a d-dimensional vector. Now from that, when you're trying to find out the partial with respect to the jth element of theta, you'll only get the term which involves the jth component. So xi transpose theta we can write as theta naught x naught plus theta 1 x1 plus theta 2 x2, so on and so forth. And when you're trying to find out the partial with respect to theta j, only the xi, the jth component of xi will exist, which is what you'll get over here. Similarly, you can simplify the expression on the right hand side, and once you just do a bit of rearrangement of the terms, you'll get the partial of the cost with respect to the jth element of theta to be summation I equal to 1 to n sigma theta xi minus yi into the jth component of xi. Now we can further just simplify. We can also just write this as yi hat minus yi into the jth component of xi. Now we could either just use gradient descent directly at this stage, or we can try and vectorize this solution. We generally prefer to vectorize the solution rather than writing d different equations, which is the next exercise. So take a few minutes, start with this equation and try and write the gradient of the cost, so del j theta with respect to del theta. Sorry, the del is missing here, so that you can then vectorize the solution. Assuming you took a bit of time to try and solve that. So we had stopped at this point. Del j theta with respect to del of theta jth is summation I equal to 1 to n yi hat minus yi into the jth component of xi. Now, whenever we're trying to solve such problems, I generally recommend just drawing out the respective matrices vectors with some simple notation which will help you to solve. So we have a matrix X, which is n rows, which means n records and d columns. From this we can try, and we'll be using the jth column, which I'm just writing as x superscript j. This is capital X and this is small x corresponding to the individual points. Similarly, we have a y hat vector and a y vector. Both of them are elements vectors of length n. Now let's look at this vector y hat minus y, and let's try and look at what this expression is trying to get us. yi hat minus yi into the jth component of xi and summed over the n examples that we have. We should try and now write this in terms of the matrix and the vectors rather than the individual scalars. So let's look at the pink component over here. We have the jth column of x. For the first example, we have the jth column and we have taken up this pink value and we multiply with this particular pink value, which is coming from the first example of yi hat minus yi. We multiply these two components. We multiply the green and the green, we multiply the blue and the blue, and then we add all of these up. Or we can then simplify this expression and write in terms of the matrix vector product something like this. We have the vector xj, which is the jth column, but we take the transpose of this. So instead of the n comma n cross 1 shaped matrix, or we now get a 1 cross n dimensional matrix, And if we do the matrix product with y hat minus y, which is an n cross 1 dimensional vector, we get 1 cross n cross n cross 1. You get a scalar, which is what you'd wanted with the correct terms being multiplied. So therefore, we can at least now vectorize the partial of the cost with respect to the jth element of theta to be the jth column of x transpose times y hat minus y. Now you should again pause at this minute and now use this expression to try and generalize and find out del j theta with respect to del theta. Now whenever we try to write this expression, one simple way to find out the answer is to just write down the entire vector as like by stacking up the different rows. The first element of this vector is del j theta with respect to del theta 1, and finally del of j theta with respect to theta d. If we write it in this way and we write down the respective scalars on the right hand side. This one is x1 transpose y hat minus y, which means the first column of x1 transpose times y hat minus y. Similarly, for the final one, we have the dth column of x transpose times y hat minus y, which if we can then try and generalize, we can write this entire thing as x transpose times y hat minus y. We can also verify these shapes. This is a d-dimensional vector. It's the gradient with respect to theta, which is itself d-dimensional, and cost is a scalar. So this is a d-dimensional vector. If we look at x transpose, its shape is d cross n, and y hat minus y is the same shape as y hat, same shape as y, which is n cross 1. So d cross n cross n cross 1 gives you a d cross 1 vector. So even from the shape analysis, we can confirm that our result is okay. Okay, so we'll now be looking at 2-3 different variants of logistic regression, some of which we have already seen with linear regression. The first is when we have to use feature transformation to get better or non-linear decision boundaries, non-linear in the input space. So if we had applied logistic regression on the above data, what do you expect to see? We see that the tomatoes are of a certain radius, which is within a circle, and then we can see on the outside of the circle are the oranges. So this is a made up contrived problem. If we were to learn logistic regression model on this data, we know that the boundary is linear. So the boundary might be a line like this. In this case, it's not a very good prediction because a lot of the points are being misclassified, but that's the best it can do because the model is exhibiting a high amount of bias. The model is not sophisticated enough at this point of time to be able to classify the two classes of data accurately. Now, this is a limitation if you just use the features directly, which is just x1 and x2. So think for a minute about how you may go and mitigate this issue. Assuming you have thought about it, you can notice that if we had instead of just using x1 and x2, we'd use higher order features, let's say x1 square, x1 into x2 and x2 square and so on, then we'd be able to get a much better classification surface, which is similar to the feature transformations that we'd seen, the basis functions that we'd seen in linear regression. Let's say if we use 1x, x squared, x cubed, so on and so forth, and we can also look at the interaction terms, let's say x1 into x2. If we do that on this problem, we'd be able to learn a much better decision surface and the classification accuracy would be much better. Now, this is not very difficult to do in code. We have already seen how to do this in linear regression. So if you see, if we come down here, we have, this was the decision surface in the earlier case, and now we have created new features which contains the features x1, x2 original features, and I've also now included the new features x1 squared, x2 squared. And if I fit on the new set of features, we can see that the decision surface is much better. Now, if we were to look at the probability contours, which is the probability of class 1, we'd be able to see them as these circular surfaces, which is again confirming that we've been able to do a good job at classification using the additional features that we had. Next, we go on to an interesting problem. Thus far, we have talked about classification, but only binary classification, which is when we only had two classes. Now, the question to you, you should think for a few minutes, is to if you're given a data set with multiple classes, how would you use classifiers such as logistic regression or random forest or any other classifier in order to get this multi-class prediction? You don't want to be just giving A versus B. You want to be giving, in this case, it's a iris data set. You're looking at different attributes of flowers, and based on that, you're trying to classify the species of the flower, setosa, versicolor, vaginica. In this case, I'm just showing the two attributes, sepal length and sepal width. There are two other attributes in this very common data set, which is known as the iris data set, which are the petal width and the petal length. So if we were to learn a logistic regression classifier, it might look like the following. Now we'll see why we may get this kind of a classifier and how to go about classifying multiple classes. Now you may be thinking that there are few ways in which we can extend our existing models for binary classification to do multi-class classification. One such method is known as one versus all binary classification. So let's say that we have these few classes, setosa, versicolor, vaginica. We can now create a separate classifier which is setosa versus the others being versicolor and vaginica. You can have another classifier which does versicolor versus vaginica and setosa, and then you can have another classifier which is vaginica versus versicolor and setosa. So these are one versus all kind of classifiers, and in these classifiers you can see which of them has the highest probability for the specific class that you're looking at, and that would be the predicted class. That's one. Second is known as one versus one method of using existing binary classifiers. Now you can build a classifier on setosa versus versicolor, and then versicolor versus vaginica, and then vaginica versus setosa. You have built three separate classifiers here, but these are one versus one. You are dealing with binary classification instead of one versus rest or one versus all, which we had seen previously. But in today's lecture, we'll be looking at a simpler method where we don't have to use one versus all or one versus one, which is we want to be extending the binary logistic regression to the multi-class logistic regression. We'll have to make a few small changes to the existing setup in order to do multi-class logistic regression. First, we'll say that let's assume that the probability of class 1 is some function of x of theta 1. So we want to retain our original setup where we first find out the logits x of theta or x transpose theta for a single point, and in binary classification we pass the logits through a sigmoid function in order to ensure that probability for a particular class 1 is between 0 and 1. So for now, let's say that we'll have some function through which we pass in the logits x theta 1 corresponding to class 1, x theta 2 corresponding to class 2, and x theta 3 corresponding to class 3. Our aim now is to learn these vectors theta 1, theta 2, theta 3. The important thing here we have to know is what this function f could be. Now, one way to think about this function f is to use the rules of probability, which were also applicable, which we also discussed briefly when we were discussing binary logistic regression, where we use the sigmoid function. So we have a few properties that probability of class 1 plus probability of class 2 plus probability of class 3 has to be 1. So therefore we need a function f which gives us summation f of x of theta I equal to 1. 1 is this property. Second, we also have to have this property that the probability of any of the class has to be between 0 and 1. It cannot be negative, it cannot be greater than 1. So thus we are looking at some kind of a function which gives us something known as the squashing properties, where we can give in any real input, Real input means minus infinity to infinity, and it will bring it down to a scale of 0 to 1. And overall, we need the setup to be done in such a way that summation of f of x theta I over the k classes is 1. One such function which we commonly use is known as the softmax function, which has these properties. So we have a z, which is, let's say, a d-dimensional vector or a k-dimensional vector if we have k classes. We have this function f of zi equal to e to the power zi and divided by the sum of e to the power zi's. So let's say we had three classes. We will learn the logits corresponding to class 1, class 2, class 3. Let's call them z1, z2, z3. And then you pass them through these functions, the softmax function. Because you are summing over the denominator, you're bringing them to a scale of 0 to 1. Secondly, because you're using the exponentiation operation, you're ensuring that the numbers are non-negative. So because of all these properties, we are able to ensure that f of zi summation over the k or the d classes is 1, where we're mentioning now f of zi being the probability of the sample being classified as class I. Now, before we go on further and look at the relationship between sigmoid and softmax, let's look at a bit of code to ensure that we understand this problem well. I'll be first showing this particular data set. So as I mentioned, I'm using the iris data set. I load the data set and I'm looking at two specific features, sepal length and sepal width. Now, if you just look at this data, it seems that the data is fairly easy to separate out linearly. So logistic regression seems like a very good fit, not a perfect fit, reasonably good fit. There is some amount of confusion between yellow and the blue class here. Now, I mentioned that we can extend binary classification to multi-class classification in logistic regression. I'll show first a naive way to do that using the torch-like setup. So I mentioned that we have to learn parameters theta 1, theta 2, and theta 3 corresponding to the three classes that we have, right? And here we are using the input dimension to 2. Our input features are of two dimensions, sepal length and sepal width. So therefore, if you remember the previous code that I'd shown, when I'd written this class logistic regression, I had mentioned that self.linear equal to nn.linear input dimension comma 1. This is basically what you get as linear regression output. And we had done that by calling this method as the logits. So this is just x transpose theta for a single x and x theta for a matrix. Now what I'm saying here is that we want to extend this to multi-class classification. So therefore, I create three different objects, linear 1, linear 2, linear 3. These would correspond to logits 1, logits corresponding to class 1, which is x transpose theta 1, then logits 2 is x transpose theta 2, and logits 3 is x transpose theta 3. So therefore I get the three logits, and as of now I'm just returning the logits by concatenating them in this function. This is one way to get three outputs, or the outputs corresponding to three different logits, or the outputs corresponding to logits for three different classes, all of them being equivalent. There is another way in which we can write this much more efficiently, is to just create this nn.linear or input dimension and the number of classes. In this case, since the number of classes is 3, it will give us the same dimensional vector as the output given a single input. We can verify this. First, I create an object of this 3-class logistic regression class, and I have my x tensor and y tensor. We can verify the shape of x tensor comma x tensor is 150 comma 2, so 150 records two-dimensional, and y has to be a vector of length 150. Now if I pass my data through this classifier, I get a vector of shape 150. I get a matrix of shape 150 comma 3, which makes sense. 150 is the number of records, and 3 corresponds to the 3 logits, or the logits for the 3 classes. Now I could have also done using the same using my second implementation, where instead of specifically learning mentioning logits corresponding to the 3 different classes and then concatenating them, I could have directly created nn.linear corresponding to the input dimensions to the number of classes. If I use that particular class and I pass in my input tensor, I get the same shape. So this is showing the equivalence between the two. Now, if I were to show what I get as the output when I pass in my input, so I'm just showing you the first 5 inputs. If I pass through this my network MLR efficient, I get a vector, I get a 3-dimensional vector corresponding to each record. Now this is the logits corresponding to the 3 different classes for the first example. Similarly, second example, third example, fourth example, fifth example. Now these logits by themselves do not hold any property. It's when we pass them through the softmax function. So I create a softmax object. I pass them through, let me just copy and show the output. Now when I pass this 5 comma 3 matrix via the softmax operator, you notice that for each of the records, each of the row, the softmax would be done firstly separately, and these numbers would now sum up to 1. So these numbers now sum up to 1. So now you can interpret this as probability of class 1 for the first example, probability of class 1, class 2 for the first example, probability of class 1 first example, probability of class 2 first example, probability of class 3 first example, probability of class 1 second example, probability of class 2 second example, probability of class 3 second example. We can now interpret in this particular way, and we can confirm that if we were to sum over the individual probabilities, they indeed sum up to 1, which means that our entire setup till now is correct. As I've mentioned many times, I think it's always a good idea to predict from an untrained model and see how your model improves once you train it. So this is some code for predicting the most probable class. It's just predicting the most probable class. You get the logits via the model, and then you do the argmax over the logits. I had mentioned this in the previous lecture also. If you just want to predict the specific class and not bother about the individual with the specific probability, you don't even need to pass through the softmax, because the softmax or the sigmoid function, they are monotonically increasing functions. So higher the logits, higher the probability. And then if we look through the probability, it shows perhaps that all the examples are classified as class 2 at this point of time for the untrained model. Now when I want to train my model, I get my logits via my model, and then I use my cross entropy loss, which works with the logits and the y tensor. And then when I train my model, and now I look at the specific logits that I get for the first 5 example. Now you can notice that these are quite different. This has become a positive number, these are negative numbers. This is indicating that for this, the first example, it's going to be predicted to be class 1. For the second example also, this is going to be predicted as class 1, etc. Now, as I did before, I can just run this through the softmax function, and once I run this through the softmax function, I get the probability of class 1, class 2, class 3. I've also put the ground truth values. The ground truth is going to be either 0 or 1 or 2. So you can see that for the first example, the probability of class 1 or class 0, so if we use 0 base indexing, is the highest, and indeed it's class 0. Similarly, for the second example also, probability of class 0 is the highest and it's indeed class 0. For a few other examples, for example, for the second last example, we can notice that the probability of class 2 is the highest and indeed it's class 2, so it's a correct classification. Whereas for the last example, it predicts the probability of class 1 versicolor to be the highest, whereas the ground truth is 2. So this would be a misclassification. We can finally get the prediction, which is the predicted class, by looking at the argmax over the prediction vector, which is a length 3 vector. And if we do that, we can notice that the predicted class is 0, corresponding to the highest probability. Here the predicted class is 1, corresponding to the highest probability. Now when we want to compute the accuracy, we just need to do a count of the places where the ground truth is the same as predicted, divided by the total number of examples, which in our case is 150. So we just do y predict equal to iris.target and we just find the average. This comes out to be 82.66% accuracy over the training data set. And now if we were to plot the trained model, we can see that all of this is predicted to be class 2, this is predicted to be class 1, and this is predicted to be class 0. It's fairly good because there are a few points which are wrongly predicted, but we would have expected that given that the model is fairly simple, the features that we're using is fairly simple, and they are clearly not completely linearly separable. So at this stage, as we've done before, we can also add some more complicated features such as x square and then x1, x2, so on and so forth. If we do that, I expand my input features from 2-dimensional to 10-dimensional and I do the same training, and now I can get an accuracy of up to 98% on my training data set. Of course, this may not be the generalization, this may not generalize well because I have not done any cross validation. I've just shown you the result on the training data set. But at least we can show that the bias has been reduced by making the feature space more sophisticated. So coming back, we had seen that we had the individual theta k vectors and corresponding to the k classes. So we can therefore write probability of y equal to k, with being the kth class, given an x and theta to be e to the power x theta k divided by k by the sum of e to the power x theta k from 1 to capital K. So this is the softmax function over the logits corresponding to the kth dimensional kth vector, kth theta vector. Now, a question for you to try and solve at this point is, can you show that for two class problems, the softmax or the multi-class logistic regression setup would come out to be the same as the two class binary class logistic regression setup where we use the sigmoid function, or how the softmax is a generalization of the sigmoid function? Assuming you spent a few minutes doing that, we can see that for k equal to 2 classes, we are just trying to simplify k equal to 0 or 1 is what we'll put. So we can, for y equal to 0, for the 0th class, we can write e to the power x theta 0 divided by e to the power x theta 0 plus e to the power x theta 1. Similarly, probability of y equal to 1 as e to the power x theta 1 over e to the power x theta 0 plus e to the power x theta 1. We can just simplify this expression and we can finally write probability of y equal to 1 given an x and theta to be 1 over 1 plus e to the power minus x theta dash. So through this, we can see that we've been able to recover the sigmoid function. In two class classification problem, it's a simple case because we only have two classes whose probabilities need to sum to 1. So therefore, just by encoding probability of y equal to 1, we automatically get probability of y equal to 0 also. Whereas for multi-class classification, we can't do that with just probability of one particular class. We can also very quickly see how this cost function would make sense for multi-class classification. Let's assume that a yi hat vector after using the softmax operation is something like this: 0 0.1, 0 0.8, 0 0.1, and our ground truth is class 2. So therefore our yi vector, if we are one hot encoding it, we could write it as 0, 1, 0. Now if we look at this expression, minus summation k equal to 1 to 3 of yi k log yi hat k. It's not raised to the power, this is just telling the kth element in that. So if we look at this expression and calculate, we get 0 into log 0.1, 1 into log 0.8, and 0 into log 0.1, which will turn out to be a very small number. Now this is happening because the true class, which was class 2, its probability is a high number. So therefore we should get a low cost. The other important thing to notice here is that the only number which contributes to the cost function is the probability of the correct class. The other two numbers, because they'll be multiplied by 0, do not even contribute. Similarly, if we had a yi hat vector to be 0.3, 0.4, 0.3, we'd expect to get a higher loss, because for the true class, the probability of it being predicted that specific class is a low number. So therefore, if we were to show the generalization of the cost function, for the two classes we had j theta equal to minus summation over the n examples yi log yi hat plus 1 minus yi log of 1 minus yi hat. So we can also notice that here we dealing with class 1 and here we dealing with class 0. If we were to generalize this to the k classes, we can simply write this as summation over the n examples and then summation over the k classes yi k log of yi hat k, where k is the kth class. You can just work this out and show that for two class problem, it's the same as the cost function that we've been using, the binary cross entropy loss that we've been using. Importantly, for two class, it's easy because we know the probability of class 1 plus probability of class 0 is going to be 1. So therefore, you can easily show the specific case of the k class cost function to the two class cost function. So I'll skip some of the more advanced stuff which we can use in order to second order methods which we can use to compute the estimates for vector theta. But I'll finally come on to the last topic in logistic regression, which is to make it regularized. Previously, we've seen in linear regression that we somehow want to regularize in order to ensure that we're not overfitting. One such way we saw that was to put some penalty on the L2 norm of theta or the L1 norm of theta. We can pretty much do the same thing here. We can use the unregularized or the binary cross entropy loss, plus we can have the lambda times the L2 norm of theta squared plus lambda or plus lambda times the L1 norm of theta. Both of these methods would give us some amount of regularization, and given that this particular function, which is a binary cross entropy loss function, is a convex function, and the L2 norm and the L1 norm are also convex functions, so addition of two convex functions gives us another convex function. So we'll stop at this point. In the next lecture, we'll see how neural networks build upon logistic regression like methods, and how we may not even need to use complex featureizers. We'll have the neural network itself learn those complex featureizers for us. Thank you.